you want me to turn on the camera as well, I guess? Let me see. Here we go.
Sure, if that's fine with you.
Okay. There's a little bit of sun in the background. Let me adjust here. Can you see? Well, let me adjust this. There we go. Let me move to this side. There's a little bit of sun in the background. There we go. All right. How are we doing today?
We are doing good. How are you?
Good, good. Thank you. How many people do we have on here? Let's see.
Right now we have 35.
Okay. And this is all undergraduate students or grad and undergrad?
Grad, undergrad, undergraduate. We also have some professors. So.
Okay, great. Great. All right.
So let's just wait like 1 more minute.
Sure. Are you just going to do an introductory kind of bio and then I can get started, right?
Sure, yeah, we can do that.
Nope. ¿Me escucho?
So let me quickly announce a few things. And then we can get started.
Sure.
So hi everyone. So let's just get started. Now I'm gonna send out a sign-up sheet in the chat box. So please fill it out so you can receive 2 points for attending this info session. And these points will help you to run for officer's position for next year. So give me a second. And the link is in the chat box, so do fill it out. And Mr. Belyadi, you can go ahead and get started if you like. Thank you.
Yep, thank you. Thank you. Well, hello, everybody. Thanks for the invite. I'm excited to present this presentation. I was asked to give an hour presentation, so I'm going to try to be as brief and precise as possible. So let's get started. Before we get started, just wanted to talk about the podcast that we have available. So if you haven't heard of this, we have a podcast called Officer Intelligence, where I invite different guests from different universities and executives and ask them about the future of AI primarily in the oil and gas industry. So if you haven't signed up to the YouTube channel, feel free to sign up. And also most of the materials that will be covered today will be from this book, Machine Learning Guide for Oil and Gas Using Python. If you have any questions, I'm pretty sure at university, you guys all have access to it. So all the materials will be from this book today. So with that being said, let's get right into it. So the first, I guess, I just didn't know what kind of backgrounds everyone has, but I just wanted to start with the basics, and then we'll go into a little bit more detail and then wrap it up with an example at the end. So let's just first talk about what is machine learning and you know, the idea behind using machine learning in the oil and gas industry. So let's first define, you know, what AI is. So you guys probably have heard of the terminology AI. So AI stands for artificial intelligence. And AI basically says using machine intelligence as opposed to human or animal intelligence, okay? So AI or artificial intelligence basically says using, you know, machine intelligence as opposed to using animal or human intelligence. Now, there is something else called machine learning, which, as you can see in this picture, is a subset of AI. So this is AI, And then a subset of AI is called machine learning. And machine learning primarily concentrates on performing a specific task, okay? And then a subset of machine learning is called deep learning. You guys probably hear the term deep learning a lot, right? Especially these days. So deep learning is basically using a machine learning algorithm referred to as artificial neural network, which we're not going to go into too much detail in this webinar. But when somebody says deep learning, is basically the fundamental building block of deep learning is artificial neural network, okay? And examples of deep learning algorithms are convolutional neural network. These are used primarily for image and text classification, image processing, and also recurrent neural network is another powerful technique used for time series analysis, time series machine learning like analysis. So just remember, just the entire point of the slide is you have AI, you have machine learning, and you have deep learning. So AI is using machine intelligence as opposed to human or animal intelligence. Machine learning deals with concentrates on performing specific tasks. And then deep learning is a subset of machine learning and is basically the fundamental building block of deep learning is ANN. Now, there's a terminology also called data mining. Now, data mining deals with searching specific information. I'm going to give a simple example. So just imagine, let's just say you're a basketball fan. Let's just say you're a basketball fan. Teaching someone how to play basketball, you can think of that as machine learning, okay? Now, finding the best basketball centers, for example, in Dallas, Texas, I live in Dallas, Texas, it is called data mining, okay? So teaching someone how to play basketball is machine learning, and then finding the best basketball centers in Dallas, Texas, for example, is referred to as data mining. So I just first wanted to spend just maybe a few minutes covering the fundamentals of AI, machine learning, deep learning before we dive into it more. Now, you might be asking, why do we care about machine learning or artificial intelligence or deep learning? Who cares, right? Now, the answer is pretty simple. As the volume of data increases, human cognition is no longer able to decipher information from that data. Like, for example, I'm going to make it simple. Let's just say you have 5 wells. You have 5 wells side by side. I can look at 5 wells and I can say, okay, I pumped this design on this well, this design on this well. You know, this well seems to be, performing better from material balance, from rate transient analysis, whatever, right? Or I can, have 1,000 wells. Now, if I have 1,000 wells, deciphering information from 1,000 wells is no longer possible with just looking at the wells. You can do simple, scatter plots of this versus that, but now I have a multi-dimensional problem, right? So I have a multi-dimensional problem. I need to train a model, especially using machine learning, to decipher important information from that data. So the whole essence of machine learning is basically finding hidden pattern, finding insight, finding information from the data. And that's what machine learning helps with, and then once I find that hidden pattern, then I can use that for optimization. Then I can use that to do other important aspects and add value for any organization. So this is slide number 1. Now, if you move on, now what is the difference between hard data and soft data? You have hard data. Now we have soft data. Now, hard data refers to field measurements, things that you actually measure and you are pretty sure about. For example, how much proppant I pumped, how much fluid I pumped. We measure these in the field. What is the pressure? We have a transducer, for example, doing frac jobs that measure surface shooting pressure. These are hard data. These are not calculated data, right? Soft data refers to as interpreted data, estimated data. For example, what is, fracture half length? What is fracture height? What is fracture conductivity? And so on. And so these are all called soft data because we calculate these. There are different techniques. You can calculate your fracture half length and height and all that, right? So these are called soft data. Now, it is preferred when you do a machine learning analysis, it is recommended and preferred to use hard data because these are actual field measurements as opposed to using soft data. So just remember, hard data is preferred than soft data. Now let's talk about different types of machine learning, models. The first type is referred to as supervised learning. They also refer to as, predictive models. So think of supervised learning. Think of a supervised machine learning model as you have a set of input features and you have an output feature or output features. You could have multiple features, okay, as an output, okay? So you have input and you have output. Now you're trying to tie these inputs to your output or outputs, okay? I'm going to start out with just a simple example. Then I'm going to go into an oil and gas example. So let's just say you're trying to buy a house, okay? There are thousands of houses in your area, okay? How do you predict the price of a new house? You can build a machine learning model, including all the houses in the area. For example, based on all the input features into your model would be number of bedrooms, number of bathrooms, garage size, square footage, proximity to school district, and so on and so forth. These are all your input features. Now, what is your output feature? Your output feature in this particular case could be price of a house, right? Because that's what you're trying to predict. So your output is what you're trying to predict. Your inputs are all the available information that you have. So you can train a machine learning model based on your input features and tie those back to an output feature with a nonlinear model. You can use linear models, but in this case, if you have a lot of nonlinearity in your data, it is preferred to use a nonlinear supervised machine learning model, right? So this is called a supervised learning. So when somebody says supervised machine learning, it just means you have your inputs and you have your output or outputs, okay? Now let's go and give an example in the oil and gas sector. So I have, let's just start with drilling, then we'll go to completions and just give a couple of examples. So in drilling, one of the key parameters is optimizing rate of penetration. And the objective function is maximizing rate of penetration, which essentially means how fast you drill a well. So your input features could be, weight on bit, differential pressure, torque, the different drilling parameters you can include in your model as input features. And your output feature, in this case, could be rate of penetration, which simply says how fast you're drilling foot per hour. So that's a drilling example. The other example is called on completions. Let's just say you're trying to optimize your EUR. You're trying to optimize your estimated ultimate recovery, okay, per foot. So there are different types of completions parameters, such as sand per foot, water per foot, cluster spacing, stage spacing, shots per foot. There are so many different design parameters during completions that you've pumped, right? You can have all of these design parameters as your input or as your inputs, and then have EUR or estimated ultimate recovery per foot as your output, and then build a supervised machine learning model. So a supervised machine learning model simply says you got your inputs, you got your output, and you can build a model then, right? This is one example. And this could be applied to anything. This machine learning is not, you can apply to any industry, any sector, for pretty much anything, right? Now, your supervised machine learning model could be regression or it could be classification. If it's regression, it simply means that your output feature is a number. You're iterating on a number. For example, when I'm trying to predict a house price is a number. So that's a regression supervised machine learning model. When I'm trying to predict EUR, or estimated ultimate recovery per foot, EUR is a number. So that is a regression supervised machine learning model. Now your output could be simply yes or no. It could be multiple classifications. It could be shale, sandstone, limestones, and so on and so forth. So you could have different classifications. So In that case, it's called a classification supervised machine learning model. So you've got regression models, you got classification models. And that's pretty much it for a supervised machine learning model. Now let's go on to talk about unsupervised model. Now unsupervised, it simply means you have a set of input features and you have no output. You have no output, okay? When you have set of input features and no output, then you're trying to cluster your data. You're trying to basically group these or group these set of features together and basically come up with a number of clusters. And examples of unsupervised learning is, let's just say in the oil and gas industry, you have 5,000 wells in a broad area, and you're trying to come up with each area of interest based on geologic features, based on, for example, design features, based on how well, how good the well performance are, and so on and so forth. You can include all of those as your input features, and then cluster your data. And then once you're done with clustering, the output of that is simply says, okay, each row of data lies under cluster 0, cluster 1, cluster 2, based on the number of clusters that you select. So example of unsupervised learning algorithms are k-means clustering, which is heavily used. You've got hierarchical clustering, density-based dbScan. There are different types of clustering algorithms that you can use to cluster your data. And clustering, so sometimes, you can cluster your data and use that clustered column as the output into your supervised machine learning model. So let's just say you have a set of features, you cluster them, and the machine learning unsupervised model will give you whether each row of data is under cluster 0, 1, or 2, like for example, and then you can use that column as the output into your supervised learning model. So you can do a semi-supervised model, which means a combination of you first cluster your data, and then you use that clustered data as part of your to build a supervised machine learning model. So this is called a semi-supervised. Then the last one is called reinforcement learning, which basically says machine learning trains itself on a continual basis. And basically the fundamental building block of reinforcement learning, let me go back here, I'm trying to move this here. The fundamental building block of reinforcement learning is that it's a learning technique that directs the action to maximize a reward or an immediate action, and those that follow. So you basically have an agent and an environment, and these two are in relation with each other, and they learn actively. So for example, let's just give a simple example. Let's just say you have a curious child in the kitchen, okay? And the child sees a knife, okay? The child uses a knife to cut vegetables, okay? So the child learns real time that, oh, wow, I can use this knife to, for example, cut vegetables. And then 2 minutes later, now the child cuts himself or herself. And then the child learns that, oh, wow, I can also use this knife. This also could be very harmful. I could also cut myself by accident, So this is basically an agent and the environment in contact with one another to basically continuously training itself. And this is the fundamental building block of reinforcement learning. So in this like presentation, I'm going to primarily focus on the supervised and unsupervised, and the reinforcement learning we can talk about it at a different time. So some examples, you have the machine learning types, you have supervised, unsupervised, semi-supervised in this case. These are different applications in different industries. For example, the housing price prediction, which I said it's a regression model. It is like under supervised. You could also have classification, which could be used for medical imaging, for example. You can use unsupervised learning for customer segmentation and market basket analysis. Examples of these, let's just say you go to Kroger or you go to Walmart, for example. Have you sometimes paid attention why Walmart or Kroger, for example, has certain items together. For example, why are the tomatoes are close to a different item? Well, they use unsupervised learning techniques to see customers that buy this item also buy this item. So to make it convenient for the customers to buy these products, what they do, they put these items together. It's like Amazon. If you go on Amazon today and basically search for, I don't know, search for a book on leadership, okay? When you search for a book for leadership, you probably get emails sometimes from Amazon, that says you might also be interested in this book. It's just another book on leadership, because Amazon uses unsupervised learning to recommend, to make product recommendations, and that's pretty powerful, because if I bought this book on leadership and I loved it, the tendency of me buying another book on leadership is probably high. So I'm gonna cluster those customers together to recommend new products. So that's what customer segmentation, market basket analysis are. So machine learning has applications in different industries. In the banking industry, for example, the fraudulent detection, the fraudulent activity. I've received calls before from the credit card company that, hey, immediately, as soon as a transaction happens in, for example, a different state, let's just say I've never been, for example, to Alabama, okay? And all of a sudden I get a transaction that occurred in Alabama. Well, what happened? Well, Wells Fargo, or for example, any of these major banks, they all have machine learning models in the background that detect fraudulent activities, okay? And immediately notify you, hey, this guy, you've primarily been in Dallas, and you've had all these transactions happening in Dallas. Now, all of a sudden, somebody purchased something in, let's just say, in Alabama. Well, that's probably not him. Let's just notify him immediately and then flag it. And then if that's the case, we can shut it down, and we can shut the car down immediately and save, a lot of money. So banks save, billions of dollars every year by using machine learning to detect fraudulent activities, to detect these anomalous behaviors within a customer behavior. And these are all good things. These are, using machine learning is just a tool to use to our advantage. If I can detect issues immediately, as opposed to not detecting them and waiting, for example, days, you could lose billions of dollars, especially the banking industry, the credit card industry. So machine learning could be used pretty much for anything, really, for different industries, and these are just some of the applications. Now, I've talked about some of the machine learning applications in the oil and gas industry. You've got completions, well spacing optimization, type curve clustering, which I touched on, rate of penetration, drilling optimization, which I touched on, predictive maintenance. When a compressor goes off, when a frac pump goes off. Predictive maintenance is pretty powerful, actually, in the oil and gas industry, to predict ahead of time, to prevent issues. Liquid loading detection, we have a paper on this. Plunger lift and intermittent optimization, fall detection, geological log prediction, facies classification, frac chemical optimization. I can go on. I just listed 10 here, but I can go probably 50, 60, 70 different applications within different sectors of the oil and gas industry. These are just the upstream sector that I'm just listing here. But these are some of the applications used in the oil and gas industry. Now, you might be asking, well, what are some of the machine learning algorithms associated with each of these techniques? I said you have supervised machine learning algorithm, you have unsupervised, and you have reinforcement learning. Examples of supervised: artificial neural network is a supervised machine learning algorithm. Support vector machine is another one. Decision tree models such as decision trees, random forests, extra trees, gradient boosting, adaptive gradient boosting, linear regression, logistic regression. These are all examples of supervised machine learning models. Okay, so these are just some of the examples, some of the algorithms within each type of machine learning. Unsupervised, as I said, you have k-means clustering, you have hierarchical clustering, density-based spatial clustering of applications with noise, dB scan, and a priori algorithm. These are some of the examples of unsupervised learning. And reinforcement learning examples are Markov decision process and Q-learning. I'm just listing some of the main ones here just for your information. Each one we have to go in detail. Of course, it is beyond the scope of this 1 hour webinar. But you know, there are different problems can be solved with different machine learning algorithms. Okay, these are just some of the examples that I just wanted you, like you might have heard of ANN or support vector machine. I just want you to know that, you know, these are called supervised, these are unsupervised, and these are reinforcement learning. Now within supervised, you could use ANN or support vector machine for, you know, like for example, for classification or regression problems. You know, so you could have a regression model or a classification model, as I alluded to in like a few other in about like two, 3 slides ago. Okay, so now let's move on to the next. Another important, it would be unfair for me to talk about machine learning and not talk about bias variance trade-off and what bias variance trade-off is and what kind of models we're interested in. Okay, so let's first define bias variance trade-off. Okay, so let's first define bias. So what is a bias? A bias simply says is the inability of a machine learning model to capture true relationship. It basically says it leads to oversimplification. Okay, so for example, if my model, this is basically this picture in the middle here. I have a bunch of points here. And if I just simply draw a straight line through these points, this is called a model that has high bias. And what it means, it basically means my model is underfitted. It's like, you know, it's like doing a scatter plot, having a bunch of points, just fitting a data, even though it's not a good fit. So it's called an underfit model. So I can do that, but the accuracy of this model would be low. So this is a model that has that has high bias. So when somebody asks what is a bias, it's the inability of a machine learning model to capture true relationship. Inability of a machine learning model to capture true relationship. Now, what is a variance? Now, variance refers to the variability of the model prediction for a given data point. Variability of a model prediction for a given data point. So if a model has high variance, it basically means it has overfitted. It basically means it has almost memorized the trends as opposed to building a general model. Okay, it has memorized the trends. So a model with high variance, low bias is not good. It just means the model has memorized everything. I'm going to give you a simple example. It's like, you know, the night before you have a test on fluid mechanics. Okay, let's go back to my college days, more than a decade ago. So you have a test on fluid mechanics. I can understand the fundamentals of fluid mechanics, understand it, learn it very well, right? Or I can just simply memorize a bunch of questions, then hoping that, you know, the test would give me those questions. Okay, you've probably all had this before. I hope this question comes on the test tomorrow. Okay. Now, if I've memorized a bunch of questions and I didn't understand the fundamental concept of fluid dynamics before my test, it just means I have a model that has high variance, which means I've memorized those trends. It's overfitted. It's almost, I'm overfitting every single point. I'm just learning those. Now I go to the test tomorrow, and guess what? The question is different. Well, the question is now different. What happened? I can't answer it. Same exact thing with the machine learning model. The machine learning model, I was able to, you know, to train a model and overfit the model with every single point. And then as soon as the machine learning model sees slightly different result or slightly different input features, it has a hard time predicting those features. Why is that? Because my model has been fitted. It has been overfitted. Means my model, I memorize those trends. I memorized those trends as opposed to understanding it. So in machine learning, the idea is to have low bias and low variance. You don't want to have high bias and high variance. You want to have low bias and low variance to have an optimal model complexity. So look at this here. So in this chart here, in this bottom right-hand chart, I have model complexity versus error, okay? Here's my bias in red, my variance in blue, okay? If I have a model that has a high variance and low bias, okay? High variance and low bias, it just means my model has been overfitted because it's too complex of a model. If I have a model that is high bias and low variance, it just means the complexity is not enough. It's not enough complexity, right? So my model is underfitted. So the idea is to have a model that has low bias and low variance right here in the middle. And this is the optimal model complexity, optimal model complexity. So you don't want to overfit, you don't want to underfit, you want to be somewhere in the middle. And this is the concept of bias variance trade-off. Bias variance trade-off. I hope that makes sense. Okay. All right. Now let's move on to the next slide. Now let's talk about workflow. How do you build a machine learning model? This is a little bit more complicated than that, but I want to try to simplify it in a few steps here. So step number one is collecting data. Collecting data. Now, you might have CSV files, SQL databases, Aries, different types of data sources that you have to collect from. Okay, so data collection is the first step. Now, what a lot of companies have done in the past few years they've been moving towards a centralized data warehouse. What that centralized data warehouse allows you to do is to have all of that information in one central place, as opposed to having this information here, that information here. Okay, it just makes it much easier to pull all this data in. If I have all my information in a cloud SQL warehouse or in an on-prem SQL warehouse, it's much easier for me to go ahead and pull that information in within seconds, as opposed to spending days. Okay, what happened to that information, that completions information? Oh, somebody left the company a couple years ago, they took it with, or we just lost it, or we just don't have it, or we have to redo the analysis, we have to redo and pull this data. When you have a central data warehouse, everything is in one place, so you can pull everything in and start your analysis immediately. Right now, or the past few years, a lot of time, I would say 80% of the time was being spent collecting and cleaning that data. Okay, and only 20% of the time is spent doing the actual analysis and doing the actual machine learning, doing the actual what truly matters. But as we move forward, as companies get more automated, have their data in one central place, that 80% that I alluded to is going to go down to like probably 10 or 20%. It's got to get to a point that it's going to be less than 5% of the time that I'm going to spend collecting that data. I'm going to have everything in one central place. I'm going to have everything automated in a manner that everything gets pulled in and I can do a lot with it. Okay. So that's step number one, collecting. Cleaning that data simply means looking at the data, looking at what's in the data, looking at just simple plots, such as distribution plots, box plots, join plots, just simple plots to understand the distribution of each parameter, to understand, what is min and max, do these numbers make sense or not? And that's a very important step. Visualizing the data is extremely important because a lot of times you could have error in your data, you could have typos, there could be anything wrong with your data, really, So for example, and understanding the data comes from your domain expertise. For example, if you know that that porosity ranges from 5 to 35%, if you have a well that has a porosity of 90%, is that a typo? Is that accurate? You have to validate that information to make sure it is accurate. Otherwise, you're going to build a model with skewed data points that are far outside your distribution, and it's not going to be a good model. It's not going to be a good general model. It's going to have a lot of flaws in it. So you want to really truly visualize your data, understand your data prior to using that data in your machine learning model. It's not just about taking a bunch of data and just like applying a machine learning algorithm. No, it's about the most important thing before you do anything with your data is visualizing, understanding your data, just getting the basic statistics. What is my min, max, median, standard deviation, all these basic parameters to make sure everything makes sense, to make sure everything from your domain expertise makes sense, okay? So in this step 2 and 3, I'm gonna go back to that slide in a minute. You have data visualization, you have anomaly detection, which means you remove the anomalous points. You have collinearity removal. And what collinearity removal simply says is that remove parameters that provide the same information. For example, if you're doing a completions design optimization, okay, sand per foot and water per foot are usually heavily collinear. So what do you do in that case? You can remove one parameter and just keep one parameter. Because if you plot sand per foot on the x-axis versus water per foot on the y-axis, usually the more sand that you pump per foot, the more water that you also pump per foot. So including both these parameters that provide this very similar information might confuse the model, right? So you remove collinear features. You drop down from, like for example, from 20, 30 features down to a certain number of features that are truly important to you, as opposed to building a model, building a massive model that has too much complexity and it's not good. So you're trying, so you got to try your best as a data scientist, as an engineer. The idea here is to try your best to reduce the dimensionality of your problem, because the more dimensions that you have, the more features that you have, the more difficult it's going to be to build a general model. So I mean, it depends on the problem, but usually that's the case. So you want to try to minimize the number of dimensions as much as you can, especially with features that provide the same information. For example, why would you include, porosity and gas in place? Well, gas in place, porosity is used in gas in place calculation. So I would use gas in place, which includes all of your geologic features into that one number, as opposed to using porosity and gas in place and water saturation and formation volume factor and so on and so forth. You just want to reduce that dimensionality. So that's very important. Collinearity removal is a very important step, which you ought to do prior to digging more into your data. And then feature ranking and selection, that's another important step, which could be tricky. Now, feature ranking and selections, you can use different algorithms to do a feature ranking, and only use features that have the most important impact on your output, okay? And remove features that have really little to no impact on your output. And that comes from two things. You can use different techniques, algorithms. You can use decision tree-based algorithms such as random forest, extra trees. You can use gradient boosting for feature ranking, and then remove features that fall at the bottom of your tree. Remove those features. Or a lot of times you can just use that with combination of your domain expertise. Your domain expertise can give you a lot of insight and information because you are the expert in this domain. If you are, for example, a drilling engineer, you are the expert when it comes to drilling. So you understand all the dynamics of drilling engineering. If you're a production engineering, you understand the dynamics of production engineering. If you're a reservoir engineer, you understand dynamics of being a reservoir engineer, right? So use your domain expertise as much as you can. Use your analytical and domain expertise as much as you can, because the combination of statistical knowledge and domain expertise is the key to building a successful machine learning model, okay? And then prior to feeding that data into your machine, prior to using any type of algorithm, some algorithms require that you standardize or normalize your data set. And what I mean by that is simply meaning that you gotta put them on the same scale. For example, if you have sand per foot and water per foot, my sand per foot ranges from 500 pound per foot to 3,000 or 4,000 pound per foot. My water per foot ranges from 50 barrels per foot, for example, to 120 barrels per foot. Well, the idea here, if I use these on two different scales, some of the machine learning algorithms, such as ANN and all those, or like, for example, support vector machine, I'm going to be biased. I'm going to have a hard time converging. So it is important to normalize the data set, okay? To be between, for all the features to be on the same scale, between 0 and 1, for example. So normalization basically says, converting the features to be between 0 and 1, and then feeding into the machine learning model, okay? So normalization basically says, converting the numbers, converting all the features with different min and max values to be between 0 and 1, and then feeding into the machine learning model. Now, some algorithms, such as the tree-based algorithms, do not require, neither normalization nor standardization. They don't require that. But some other Euclidean-based algorithms, they do require that. So you've got to see which algorithms requires it, which algorithm doesn't, okay? And then go from there. And we're going to talk about the standardization in a minute, but before we go there, let's just talk about the step 1, 2, and 3. So now you've normalized your data. Now you can use that normalized or standardized data set to feed into your machine learning model. Let's just say you chose one specific model. Let's just say you chose support vector machine model, okay? Now, the idea here is to divide your data into training set and testing set, okay? Let's just say you feed your data with 70% of the data as training, and then you're gonna test it on the remaining 30% of the data, okay? So you got training and testing. First, you train a model on that 70% and get the R square for that, okay? Get the R. Let's just say you train a model, your R square is, let's just say 85%. Now you apply that trained model to the test set, which is the 30%, to see how your model basically holds up. If your test R square is also close to 85% or even better, then this is one way of validating your model, right? And then another step is to completely, what I would do is completely take another blind set that the model has never ever seen before and apply that trained machine learning model on the blind set to see how it performs on the blind set. And if that also does well, then great. Let's just say you train a model, your training set, your training R square is 95%. And you're testing and you go apply on the testing set or the blind set, and your blind set, let's just say, is 60%. This simply means you have trained an overfitted model. Remember, I talked about the bias variance trade-off? You have trained an overfitted model, which basically means that you have high variance and low bias. And this is not good because it's like memorizing. Remember the example that I gave, memorizing your test as opposed to understanding the fundamentals of your test or understanding the fundamentals and concept of that topic, right? So if your training set is 90% or 95% and your test or blind set, for example, turns out to be 60%, means you have built an overfit model. This is not good because, on paper it looks good, but as soon as you go apply it on something that the model hasn't seen before, then you've got problems. You might say, well, Haas, what do I do in those cases? Well, you got different techniques you can apply to. One thing you can do is maybe add more data. You might say, I don't have more data. Try a different algorithm. Fine tune those hyperparameters. You have hyperparameters within each algorithm. For example, ANN. You can have what kind of activation function you want to have, how many neurons you want to have, what kind of solver you want to use. All of these hyperparameters within each model can be fine-tuned, can be optimized. This is beyond the scope of this webinar, but you could do those things, So you don't want to have an overfitted model, which means you train it, it's 90%, you test it, is 60%, 50%. That's a problem. Now, what if you, so the idea is to make sure that your model holds up. If your model doesn't hold up, somebody's going to ask you, what kind of a model is this? Because it's not going to work out. It's not going to do a good job predicting. So that's why it's very important to, make sure that you test the model and make sure the model is actually holds up on various blind sets. Okay. And then I talked about the testing the model. And then there's another thing that I'm not covering here is the grid search. You can do grid search to optimize the hyperparameters within each machine learning model. This is another optimization technique. And then finally, once you've built and optimized your hyperparameters, the last step is you can do one more thing to understand what is the optimum features, what is the optimum values for each feature in your model. For example, if you're trying to understand what is my optimum sand per foot, what is my optimum water per foot, what is my optimum cluster spacing or stage spacing, that's when we go to optimization. And optimization is when you use different types of algorithms, such as genetic algorithm, particle swarm optimization, which we actually have, we have covered this in the last chapter of the book, how you can actually apply genetic and particle swarm optimization within Python in the last chapter of the book. So you can apply those techniques to find your optimum features, your optimum values for each feature, which is the most important thing that you're trying to find. Okay. So again, as I said, I try to kind of break it down and make it as simple as possible, but there are a lot of steps within each step. So now let's go on and show you just this is, there are different libraries in Python. I don't know how many of you guys have used Python before. So Python is basically a programming language. It is a programming language that has many different libraries in it that has simplified the process of coding. You have, for example, the scikit-learn library is a machine learning library used to apply different machine learning algorithms. TensorFlow is a deep learning library in Python. Seaborn and Matplotlib and Matplotlib and Plotly, these are visualization libraries in Python. NumPy is basically allows you to do a lot of the linear algebra in Python. Pandas is basically the equivalent of Excel in Python, used for data processing, data pre-processing, aggregation, all kinds of stuff. So there are a lot of very powerful libraries in Python that have made this entire process super simple. So if you are in college, I'm assuming a lot of you guys are students, undergraduate and graduate students, highly recommend to learn Python. Highly recommend it. If you stay in the oil and gas industry, or if you go to any other industry, it's very powerful. You can automate your tasks. You can do a lot of work in no time. And it's just, there's so much in there, and it's an open source platform with a lot of information online. If you're typing a few lines of code, you get an error, you can always look it up on Google, and you can find a ton of information on it. So highly recommend it, especially if you're a college student, or if you're going to graduate in a year or two. So anyways, so I'm getting off topic here a little bit. So on the right, on the left hand side, this is simply plotting each variable versus another one, just to see just to see if you can find the anomalous point in each variable. Again, this is really you really have to zoom in and into this to see what's going on, And on the right hand side, This is basically a heat map, okay, that shows different geological properties. For example, porosity, total organic carbon content, fluid volume per foot, proppant per foot, treating rate, 100 mesh, and so on and so forth. Versus another one, versus each one basically. So this basically says that parameters that are heavily collinear can be removed. For example, in this case, you can see here, fluid volume per foot has a 0.77 Pearson correlation coefficient with proppant per foot, okay? It just means that when I pump higher proppant, I'm also pumping higher fluid. So it's a decision for you to say, do I want to keep both parameters or not? Or you can always train two separate models. Train a model with proppant per foot, and train another model with, a water per foot. Okay. So this is simply a Pearson correlation coefficient, which stands for R. And Pearson correlation coefficient basically says it's the covariance of X and Y divided by standard deviation of X times standard deviation of Y. And that's how you can do this in Excel, but with one line of code using the Seaborn library, you can generate this plot, which is the beauty of Python. The beauty of Python is that you can generate these plots with one or two lines of code in Seaborn. SNS.heatmap. In this case, you just type in SNS.heatmap, your data frame dot correlation dot CORR, open and close parentheses, and then you just generate this heat map with one line of code, which is pretty powerful, as opposed to going into Excel and building a matrix in Excel. You can do all of this in Python. So if you're in college, I highly recommend using Python and starting, at least if you haven't learned like how to use Python, start, learning the fundamentals and going deeper and deeper into it. So I talked about feature normalization and standardization. You might be asking, how do I normalize my features? Well, it's actually pretty simple. You take each input feature minus the minimum of that column, divided by max minus min, and that basically converts your each feature to be between 0 and 1, And feature standardization is simply taking each feature minus the mean divided by the standard deviation. And with feature standardization, you're basically trying to standardize your data to have a mean of 0 and a standard deviation of 1. So if you take that entire column after standardizing it, it's going to have an average of 0 and it's going to have a standard deviation of 1. So it's on the similar standardized scale. Okay. So this is feature normalization standardization. Now, as I said, the major mistake that many corporations make have been hiring either statisticians without, or the major mistake, in my opinion, has been not combining the domain experts and the statisticians or AI experts, for example. The key to success is truly combining the domain experts and people that have strong mathematical background. That's the key to success in having a very good machine learning model. So the true value is created when you combine these two. So if you are a hiring manager, if you are trying to start a department, like for example, teaching, taking on different machine learning projects, highly recommend to combine people with strong domain expertise in that industry and combine those people with people that have strong mathematical statistical background. Now, I also want to talk about data centers. You probably hear about data centers, like for example, the most important ones that you guys hear about is Amazon, AWS, which is a huge portion of Amazon, like corporation itself. So what is it? Let's first talk about what is a data center. So a data center basically houses servers and data storage for an organization. Okay. If you go inside of a data center, you have hardware, the space where the hardware is housed, power, backup systems, environmental control that needed to keep all the servers running. Okay. You could have a single server or hundreds of servers in a data center. Okay. Companies such as Amazon, Microsoft, Google, they offer public cloud computing that have cloud data centers that are available to various organizations. They're available to various individuals or organizations. Okay. So a data center basically is where all the stuff is stored, where all the hardware, all the power, backup system, environmental controls, everything is stored. So you could have two types of data centers. You could have on-prem data center, which is a data center managed by a corporation. Okay. Or you could have cloud data centers, which are third-party data centers managed by Amazon, Microsoft, Google, and just go with those guys. Now, the on-prem data center, so the on-premise data center, you could have an on-prem data center, but it requires, it's owned and managed by the organization in question for their own internal use. And of course, it requires a lot of IT folks to manage that. It's a lot of work. When things break down, you're responsible for changing the hardware. You're responsible for maintaining it. So there's a lot of ongoing maintenance costs with the on-prem data center. Now with the cloud, it's a scalable model. With the cloud data centers provided by Amazon through AWS, Microsoft through Azure, Google. These are scalable models, which means they're managed by Amazon, Microsoft, and Google, and so on and so forth, as opposed to having an IT department managing it for you internally. So it's a scalable model, and it is what has been very common in the past. I would say like five to 10 years now. So if you look at the advantages here, the traditional data centers, you have complete control over hardware. The advantages are cost of use is easier to understand. Privacy can be maintained, of course. Disadvantages, with traditional data centers, you have high upfront cost. It takes a lot of space, uses power, whether used or not, requires a dedicated team to maintain. You have an IT team to maintain this. Hard to access remotely. Security solely dependent on local team. If you have a strong IT team, you might have a secure system. Otherwise, you could not have a secure system. And updates are not automatic. Rely on the local IT team, right? Now, cloud computing, little upfront cost. You can get into it really fast, quickly. I can sign up for it on Amazon. Amazon has all the hardware. Amazon has data centers. So when we say cloud, it doesn't mean that Amazon doesn't have data centers. Amazon, it basically means that Amazon or Microsoft or Google, they manage it for you. They've built the infrastructure. They have, you guys have probably seen underwater data centers that a lot of these companies have. They have massive data centers, but they manage it for you. They do all the updates, all the work that you don't want to do, they do it for you. So it's little upfront cost, okay? It's a scalable model. It's the key here. I want you to understand that it is a scalable model. If you're a company, you're a startup, you want to scale up, as opposed to buying all this, investing all this money into this upfront cost, which a lot of people don't like. You can just go into an Amazon, boom, boom, and scale is a scalable model and basically be in a very good shape. And it's also, you pay for what you use. You only pay for what you use. You don't just, like with the traditional data centers, you got to pay for the space, you got to pay for power, whether you use it or not. With the cloud computing, with the cloud data centers, you pretty much you pay for what you use. Rapid implementation, easy to access remotely, independent platform, automatically updated, ongoing security. Now, you have less control over the actual hardware and operating system. You have to pretty much go with what Amazon or Microsoft and those guys provide. And sometimes the cost structure can be a little bit hard to understand. That's one of the complaints that I hear a lot about the cloud computation. in the cloud data centers. So this is something to just keep in mind, that the cost structure can be a little bit tricky. So some organizations have both traditional and cloud computing, which I have the advantages and disadvantages on the right hand side here for you. Now, finally, to wrap it up, I know it's been almost an hour that I've been talking, and you guys are probably ready to be done with this. So I'm going to wrap it up with, as I said, I apologize. This has been, I only have an hour. There's so much to cover here, but I just wanted to show you, after we build, let's just say I built a machine learning model, and this is an example that I just took from the book and I put it here. You can do different sensitivity analysis on what is the impact of each feature on my, for example, in this case, EUR per 1,000 feet, like in this case, estimated ultimate recovery. So you can see here, I have stage spacing, I have water per foot, I have prop and loading, I have thickness, I have my well dip, I have my lateral length, percentage of lateral, like in zone, porosity, and injection rate. You can see here, for example, let's just look at the top, like first row. As you can see here, as I increase my stage spacing, as I go from 140 feet in this case to 180 feet, there's a clear degradation in my EUR. As I increase my water per foot, you can see a clear increase in EUR. And as I increase my prop and loading, very high increase in my EUR. So this is after training a model. So after training a machine learning model, I can sensitize on different parameters to understand what is the impact of each parameter on my output feature, which in this case was EUR or estimated ultimate recovery. And on the right-hand side here is another picture. For example, I have prop and loading on the y-axis. I have lateral length on the x-axis. And the numbers that you see within this heat map here is basically the EUR. So as you can see, higher prop and loading, in this case, up to 3,000 feet, and higher lateral length up to 9,500 feet resulted in the highest EUR. This is just an example that we're using in this book. You can sensitize on different parameters. The last part of this is to use genetic algorithm or different types of optimization algorithms, such as particle swarm optimization, to find the optimum features for each of the features that you use in your machine learning model. And here's another figure here that shows, for example, lateral length and prop and loading. And again, it shows higher prop and loading and higher lateral length results in highest EUR. So again, this is all done in Python. This is all done with different libraries that we use in Python, scikit-learn, Seaborn, Plotly, and all of these have been summarized in the book. With that being said, that's all I have for today. I appreciate you guys listening. I would leave it up to any questions you may have.
Mr. Belyadi, there are 2 questions in the chat box.
Okay. Here we go. All right, so should we try to cleanse the data in the Excel sheet itself before? No, you wouldn't do it in Excel. You can use Python. Pandas, like Python Pandas library is very powerful for pre-processing and cleaning the data. I mean, you can do it in Excel if you feel more comfortable, but I highly recommend learning how to do it in Pandas so you can automate your tasks as opposed to using it in as opposed to doing it in Excel. You can do filtering, all kinds of stuff that Excel does, way more complicated stuff within the Pandas library. So if I were you, you could do it in Excel, but I would recommend using Python Pandas, P-A-N-D-A-S library. Question number 2, if I have to numerically index categorical data, would you recommend representing on a random user-defined numerical scale, or should we create dummy variables? You could use, if I have to numerically index categorical data, would you recommend representing on a random user-defined numerical scale, or should we create dummy variables? I would use, I mean, you could do both, but I would try using the dummy variables to see what it does. And then it really depends on the problem, honestly. Now that I think about it, but if you provide me more information about what you're trying to do, more insight into what you're trying to solve and what your problem is, then I can provide more insight into this. I think it'd be hard for me to provide an exact answer, not knowing more background about the problem. Any other questions?
Hi, Mr. Belyadi.
Yes, sir.
How are you doing?
I'm doing well. How are you?
Good. Thank you so much for your informative presentation. It's really, really helpful. I know that you worked a lot in oil and gas field and deal with many projects with other guys such as Dr. Mohammed and other guys. For me, the thing is that the data science and machine learning, all of the times in any webinar or address or any books, all of the guys, talking about the benefit, the positive, points about the machine learning and data science. But the thing is that when you go from the theory to the real, positions in you right now, you wanted to start with the real data in oil and gas company.
Yeah.
What is the main, challenges you may deal with? And you have a lot of experience with that projects. And what do you think? What is the main source of erroneous or deviation from the normal things, and what is the recommendations and remedy for that issues? Thank you.
Yeah, that's a great question. So, and that's the problem that I think, especially is it was very common in the oil and gas, like a few years ago, because nobody wanted to share their data, right? Now, I mean, there are a lot of publicly available data sets that you could use and are publicly available. For example, one of them is called MSEAL, which is a project between Department of Energy, West Virginia University, and a company, I believe, called Northeast Natural Resources or Energy, that has a lot of the information from seismic to drilling to frac information, all available. If you just type in MSEAL, MSEEL, you can have all that data set available. We actually use some of that data set in the book, or you could use other, I think Equinor, they actually release some information, like the Volvo data set. You could use Equinor's Volvo data set as well. Now, it is challenging because a lot of companies, of course, for obvious reasons, they don't want to share a lot of the data, right? Because they want to have a advantage over everybody else. Like in my mind, the best thing to do is just to use what's publicly available. And there are a lot of, and I think more and more people have started opening up and sharing information on GitHub and other like platforms, like for the oil and gas industry, that you could potentially use. There are a lot of also state data. A lot of state data are usually pretty accurate. For example, in Veris and like in those guys, they do a very good job compiling all the state data from different companies in different basins, and providing a very good data source for all that information. If you are at the university level, I highly recommend reaching out to them. They can definitely, I think that they will be happy to partner with different universities to actually provide you their platform to use. And they have a lot of good data that is QA QC'd. That's another option. I think you guys at the university have a very good public advantage to getting in touch with a lot of these data providers, especially in the past few years, like Inveris, which used to be called RSEG, which just bought RSEG, has a lot of that information. So you could get in touch with them, especially if you're trying to use that data for different machine learning projects within the university or for teaching purposes. You could definitely reach out to them and tell them about your project and plan. I'm pretty sure they're actually looking for some university partners to partner with them and basically use that data. So even though there are some publicly available information available that you can use, you could also reach out to some of these companies, especially you guys are at the university. A lot of these companies would love to partner with you guys and provide you guys that data.
I was wondering, this is Jim Browning. I was wondering if you could cover a couple things real quick. One is, can you tell them the perils of automated data cleansing? Because there is the issue, you got to make sure that you don't insert bias into your, you scrub the data.
You said the power of automated data cleansing, is that what you said?
No, the perils. The perils, because you can basically insert bias, because you may have data points that while they appear to be outliers, the reality is that they're important data. So,
yes.
So I want to make sure, because that's one of the issues that we have with students, is they scrub the data to look so pretty that it erases what's happening.
Yes, yeah, that's the fair point. So when I said, if you go back to the slide or one of the slides that I covered, and I said you've got to visualize the data to understand whether that data point is valid or not. If a data point is not valid because it's completely out of range, and we know that from your domain expertise it doesn't exist, it's impossible to physically exist, then you can remove those bad data points, right? Due to typos or stuff like that. But if that data point is actually good, if that data point has no issues with it, and it's just a test that was done, and just because it's out of range, it doesn't mean that you should remove that data point. So I would not recommend removing data points that are actually valid and good data points to make it look pretty and to have a pretty distribution plot. What I would recommend doing is, for example, if you have a log normal, if you have a log normal distribution, you can apply different techniques to make that log normal distribution and transform it into a normal distribution. A simple technique, just apply a log base 10.
Well, transforms are very helpful, yes. But the concern is that there's a reason why the data is ugly. It may be because your domain expertise is an important point here, because one of the things that comes out of it could be the reason that it's ugly is because you're not taking into account the right factors or whatever. So and that's one of the things that I want to make sure that people hear, because one of the things that I've run into with students and with people writing technical papers is by scrubbing it, they simplify the data to where it's not realistic.
Yes, that's a very valid point. And as I said, combining domain expertise with people that have statistical background, that's the key to success. And you're right that a lot of times people just with no background, they just want to massage the data to make it look pretty. And in reality, it doesn't work. So that's why, your domain expertise, or if you don't have a domain expertise, for example, get with somebody who has domain expertise, get with somebody and ask, hey, for example, Kevin, what do you think about this point? Or, hey, Jeff, what do you think about this point? Does it make sense? Does it not? And verify it with them. And there will actually be I mean, in the past 10 years that I've been in the industry, everybody's very helpful, like in terms of verifying good and bad points to make sure when you build a model, it is a good model. So yeah, absolutely. Reaching out to people, verifying the data, and spending that time. That's part of the data pre-processing that I highly recommend everybody to do. Spend a lot of time understanding the overall data that you have prior to digging into just applying a bunch of algorithms to train a model.
Thank you. That was my point, because we see so much of a desire to oversimplify, and that the domain expertise is important also when you're dealing with public data. You have to understand the data you're dealing with.
Yes, sir. Yep.
Thank you.
Yep, you're welcome.
Mr. Belyadi, we have another question in the chat box.
Okay.
So Ibrahim, I'm sorry for getting delayed. So his question is there any way to know that we have enough data for the machine learning model? I'm working on fracture diagnostic tests that it's hard to get a lot of data series.
Yeah, I mean, that's unfortunately the problem with one of the main disadvantages of using machine learning, right? If you don't have enough data, it gets harder. So the question is, how do we know that we have enough data? Well, let's just say you train a model and your accuracy of that model is very low. You could do two things. One is you could add more data, as I alluded to in the presentation, or you could try to fine tune your hyperparameters to optimize those hyperparameters to have an optimal model. But at some point, no matter what you do, you just don't have enough data. So if your model accuracy is low in terms of your testing and blind set, it could simply mean that you just don't have enough data, and you cannot, use machine learning in this case to perform your project. Now, there are different techniques that you could apply to get to that point before you make that conclusion. But usually, if your model accuracy is low, it just means that it's going to be very hard to build a solid model. So how do you know if you have enough data? If you can build a model that is solid, that has high accuracy and low root mean square error, for example, and you're satisfied with how everything looks, you do a sensitivity analysis. I highly recommend performing sensitivity analysis to figure out whether the overall trends make sense or not. If everything looks good, then you're in a good shape. Otherwise, you've got to, start, maybe including more information into your analysis. Any other questions? So the next one, as a follow-up, there's also the concern of how to effectively normalize the fracture diagnostic tests, which may be necessary for analysis. When you say how to, let me see. So if my question is about a topic, but what do you think about?
The normalization is that fracture diagnostic tests they're blobs.
Mm-hmm.
They're large chunks of data.
Mm-hmm.
And that's part of the problem that Ibrahim was talking about, is the difficulty. They're expensive tests.
Mm-hmm.
But the problem is that they may not, there needs to be some care to make sure that you like comparisons, and to do a norm. You may have to do some level of normalization, but you got to be careful that this is part, when you're talking about normalizing the data, you got to be careful that when you normalize it, you don't destroy it.
Yeah. So in that case, I mean, I would highly recommend, depending on what type of algorithm you're trying to choose. Do you know what kind of algorithm you guys are choosing for this project?
Ibrahim, that's you.
If you can define what type of algorithm, depending on the algorithm, like for example, if you're going to use a neural network, you have to normalize your data. Otherwise, your model will be biased. If you're using tree-based algorithms, you don't need to normalize or standardize. It really depends on the type of algorithm that you're going to use. But if you use a lot of these supervised models, a lot of them do require either normalization or standardization. And basically the whole point of normalization is to have everything on the same scale so your results are not biased. And also a lot of times, a lot of these algorithms will have a easier time converging, to the optimum point. Because the objective in a lot of these algorithms is minimizing or maximizing an objective function, right? And that objective function to be minimized or maximized, they work much better when your data is in a normalized setting. I hope that answers your question.
That's. I was just trying to point you, help Ibrahim a little bit. So we'll see if that works for him. Thank you.
Okay, you're welcome. All right. Good deal. Looks like these are all the questions.
Got a
We have
couple
one
more
more.
questions.
There's more question?
Is there a specific reason for selecting 70-30% for training and testing?
No, there is not a specific reason. You could, this was just like a lot of the stuff that I mentioned throughout this presentation were just examples. Like when I say 70-30 split, you could try 80-20, you could try 75-25, you could try 90-10. You can also take out a big portion of your data as a blind set, for example. You could try different splitting percentages, and see how the algorithm performs. And you can also do cross validation if you just don't want to do a train test split, in the scikit-learn. I would also recommend using cross validation where you do, 5-fold, or if you have the time and your data source is not big, you can use, or your data set is not big, you can use a 10-fold cross validation, which takes longer. So you can use cross validation as well, in addition to train testing split, to build your optimal model. So you can do different types of techniques to do that. And the 70-30 was just simply I was just trying to, break down the concept and just said like 70-30.
Hello, I am Ibrahim. I just wanted to to follow up on my question. I had troubles with the computer, so I just want to ask, because like I said, that getting data from DFIT, it's not easy. I have a bunch of data.
Okay.
It's I don't think it's gonna give me a good model. So it's is there a test that you can make so that you have enough data, or the minimum at least?
Let me ask you this question. What are you trying to do? What's your objective with this DFIT? What are you trying to build or predict?
Basically, the data series that I should have is just time against pressure.
Yes.
And try to get the minimum horizontal stress or the closure pressure.
The closure pressure. So you're trying to predict closure pressure from time and pressure from your DFIT, right?
Yes.
Now, how are you going to, because the closure pressure is usually obtained from different diagnostic plots in DFIT, including G-function plot, log plot, and square root plot, right?
Correct.
So my question is, so you're using time and pressure as your input features, and then you're using.
I mean, if I'm gonna do analysis for each test and get that closure pressure, that means it's gonna be.
I see.
Because it needs a human to draw the tangent and do everything.
Correct.
I don't think any machine learning algorithm will do what humans need to do.
Right, right. So you're drawing a tangent on your G function plot. You're obtaining your closure pressure from your G function plot. Then you're using that closure pressure obtained from your G function plot as your output into your machine learning model. Am I correct?
Yes, something like that. Yeah.
Okay. Now, so it's going to be a fixed output for the entire DFED duration.
No, but like I said, it's gonna be a time and pressure. You know,
Okay. What algorithm are you using to do this?
I don't know. I mean, I'm just. I want to know if I can apply machine algorithm up on this I mean task, because what I'm doing right now is basically analytical techniques, you know, but
Yeah.
I want to include some of the machine learning algorithm. Maybe at least I mean no one ever come to this area with the machine learning algorithm.
Yeah. So you
The,
could, yeah, if I may. So you first have to define your input features and your output feature. So just saying time and pressure as my input feature and output would be closure pressure. I think it's almost impossible to build a model like that because you need more input features, you know. Now you could if you have, for example, defects from hundreds or tens of wells, you could, for example, have um, you know, pressure and a bunch of other input features, and then have one closure pressure per well. You could, you know, so each row of your data would be on a well level. But if you're trying to build a time series model where you can predict closure pressure from time and pressure, um, to be honest with you, it'd be a little bit difficult. I'm not sure. Like I'm trying to think. I mean, this is not an impossible problem to solve, but it requires more thinking and thought process behind it. You know.
what if I wanted to add like some logging data for the like as an input, and in the end of the day you need to estimate or come up with a model that predicts the minimum horizontal stress, which basically,
okay, why don't you do this? Here's what I recommend you do. If you're trying to predict minimum horizontal stress, okay, and instead of using DFED data, why don't you use sonic data? Use sonic data. The sonic data has you can actually, what you can do. Here's what you can do actually. So you could use porosity, resistivity, bulk density, and bunch of other parameters from your sonic as your inputs. And you can use your shear wave and compression wave travel times, okay, delta TS and delta TC, shear and compression wave travel times. Those are the two columns that you can use as the output into your machine learning model. And then once you predict your shear and compression wave travel times, you can calculate your Poisson's ratio, Young's modulus, and minimum horizontal stress, which is your closure pressure. I would go that route as opposed to going the DFED route, which might be much more complicated. Actually, there are a ton of papers on this. Actually, we actually have an example on predicting compression shear wave travel time in the book in chapter 5. There's a supervised example on that. I would go that route.
interesting. Definitely I would look at that. Thank you very much. Thank you.
Yep. You're welcome.
Mr. Belyadi, there was one question that was left behind. So I'm just going to read it out to you.
Okay.
So the question is, what do you think about Oceanit fully automated directional drilling? Do you think that AI will replace the specialists anytime soon?
I think like eventually a lot of the drilling and even, I mean, I don't know how long it will take, but I think a lot of the drilling and completion processes, including calling the frac jobs or doing the directional, will be automated with minimal human intervention. A lot of people might disagree with me, but I think that's the beauty of, you know, having a lot of data and using deep learning and TensorFlow to perform such tasks. You know, so I think over time those processes that were once thought to be impossible would be very much automated, and I think they would do a much better job than a subjective human being, you know, calling those jobs.
sorry to butt in, but that's already being described in the literature. That specialists aren't, with the specialists being remote. So eliminating, they're basically the online specialists are in the process of being eliminated, but or the on-site guys, but the remote guys are still going to be needed. So that's what's are being published and advertised. They're discussing that at OTC 2 weeks ago.
Yeah, I mean, I guess what I meant to say was like for example, in hydraulic frac jobs, you still have a company man that is in the frac van calling the job that says, okay, let's go from half a pound, proppant concentration to 0.75 to 1, or let's increase rate, let's increase FR, let's reduce FR. All of these, step-by-step subjective decisions that are being made on the fly have not been automated yet. And those, I think, will eventually get automated. Right now, if you go and tell an operator that we're just going to let a machine learning model, decide how much FR you're going to run, what kind of rate you're going to pump, how much proppant concentration you should stay at, I will tell you 99% of them will tell you, no, we can't do that. It's too risky. But I think over time, as we get more comfortable with AI and have more data, that process, especially not having a company man on site, calling these frac jobs or completely automating that will happen, I think, over time. It might take 5 years, it might take 10 years, but I think it will eventually happen because this is just simply a decision tree process. And I think it could very well happen. It takes a bit more research and time to get there, but I think it will happen. Why is it more to have a human making those? It's not risky. It's just, it's not, well, first off, I think, here's the example that I give. If you have a doctor with 30 years of experience, okay, let's just say the doctor has seen, 10,000 patients, throughout like 30 years of experience, okay, and then, the doctor is very reputable, top notch in his field. Would you trust that doctor to give you recommendations on what to do on your health versus a machine learning model that has seen, billions of, or let's say millions of patients, in that regard? In my opinion, I think the machine learning model would do a much better job than a doctor that has, seen, for example, 10,000 patients. Although the doctor has a lot of experience, but I think the machine learning model would definitely outperform like a doctor. Same concept here. In, for example, hydraulic fracturing. If I can train a model with different behaviors from different fields, from different basins, with different behaviors that have been observed, and basically build a good general model, I think that will do a much better job than somebody with limited amount of experience in the frac van subjectively calling the stages. That's what I think the difference is coming from. Now, as I said, it takes time. It takes a lot of research to build these automated models, but I think we'll get there.
Mr. Belyadi, I know we are a little over time, so if you would like, you can call this the last question, and we don't want to take a lot of your time.
All right, sorry, my background is, I forgot when I started this presentation, it was lights and now it's dark.
It's okay.
Sorry about I need to turn on my lights, but it was very light when I started this presentation. So what's the last question?
We don't have any in the chat box yet.
Okay. All right. If there are no more questions, I appreciate everybody's time. Thank you for listening, and I'm on LinkedIn. So if you want to add me on LinkedIn, if you have any more questions, feel free to reach out to me. Be happy to answer any questions that you may have.
Well, thank you so much, Mr. Belyadi, for all the information and your time. We really appreciate you, and we really enjoyed you having as our guest speaker. And I also would like to thank everyone for being here today. And if you would like to follow him on LinkedIn, I'm going to send out the link in the chat box right now. And I'm also going to send out the website link of this company, Obsertelligence. So you can definitely visit that for more information on data science and artificial intelligence.
Yep. Thank you so much. Appreciate it.
Thank you so much.
Thank
Everyone
you.
have a great night.
Thank you. Bye-bye.
Good job.